So I guess I normally start these sorts of speeches, actually I've done it for many years, for inquiring how many people have used speech recognition systems? Show of hands. Oh, actually that's disproportionately small. How many people, none of you have used Siri? Google Talk? No? Okay. How many of you, almost feel like giving up. How many of you actually think that it worked well? Okay, actually so, a slightly disappointing percentage have used it, but a slightly larger percentage think that it worked well. So that number's varied over the years. Normally, slightly exception, normally the number who've used it have been going up over the year, and in fact the number that have been enjoying the process of using these speech recognition systems has also gone up. So this all kind of started, in many ways, sort of people, a lot of the knowledge of the general population for speech recognition came about with Apple introducing Siri in 2011. Those of you may not recognise this was a UK advert with Kevin Bacon sort of telling us all about the joys of Siri and how wonderfully it worked. If you actually look for the spoofs around that time, there are some interesting ones which actually finish with the tagline, Siri, it sometimes isn't. So, loads of speech application areas. There's input devices, communication devices, information retrieval. These days it's ever increasing. You've got all sorts of things where you've got Amazon Echo, Google Talk, you've got spoken machine translation, all sorts of aspects based around speech recognition. And on the whole, speech recognition these days, when you look at Siri, the issues with it are nothing to do with the speech recognition a lot of the time. It actually is pretty good. It's the natural language understanding scenario that goes a little bit wrong with it. But that doesn't mean that speech recognition is solved. It's not bad, but you've actually got lots of scenarios. For example, in the bottom left-hand corner, we've got, is there a laser on this? No. In the bottom left-hand corner, you've got meeting transcription. We don't have meeting transcription systems at the moment that work incredibly well. We can't just place a microphone in the middle of a room where there's a meeting taking place and it will generate a verbatim transcription of what was said, let alone the downstream processing that you might like from it, such as summarization, pretty print, who said what when. So speech recognition, quite easy, nice proof of concept. We have speech production. We do speech synthesis very well. I'm doing it now. Very much a physical, well, I hope the laughter was because I was. Speech production, we just run with it. We talk, and then we listen. And on the whole, it works incredibly well. And then we understand it all. Proof of concept, it works. We have nice end-to-end systems that all operate. So you kind of say, should we just be building giant ears for speech recognition systems? And of course not. It sort of goes very much along the lines of flight. On the left, we have Icarus, who flew too close to the sun. In the middle, we have the Wright brothers that sat there and basically produced a very simple plane. And on the furthest right, we have an A380, which actually, when I produced this slide, was popular, but now not so much. So basically, I'm an engineer. I really don't care about trying to reproduce the speech production process, the speech recognition process that goes on in humans, or even the understanding process. All I care about is solving the problem and using whatever comes about that allows me to do that. So what's the actual approaches that we go about using for this? So this is what we want to do. So just to prove that I really am an engineer, this is, anyone recognize the language? Any guess? Correct, wrong. No, it's Zulu. And just to prove this, actually, I worked on the Babel project, lots of different languages, of which I spoke absolutely none of them. And so what we did, we actually did this, anyone actually recognize this? I did drop it into Google Translate. It's something about gas that they bought. Apparently, gas cylinders are a very dominant theme in various Babel languages. But this is all that we want to do in speech recognition. We're just going to take a waveform at the top. We want to convert it into words at the bottom. And I'm actually going to assume, for all of this, that I've got some mass of supervised training data. By that I mean I actually have reference waveforms, I have reference word sequences, and I'm just going to learn the mapping between the two. And that's the whole task. Don't care how humans do it, I'm just going to run as an engineer and try and solve that problem. So I'm now going to describe quickly the sort of traditional approach that goes on. And in fact, it's the approach that really, when people talk about deep learning for speech recognition, it's kind of what they're slotting into for the majority of systems. So the first stage is we take that waveform and we generate features from it. Typically, those features are every 10 milliseconds. So we take a 25 millisecond window, every 10 milliseconds, parameterize it. Well, normally filter bank coefficients, you basically just run an FFT on the waveform. You then have nice triangular filters placed on top of that frequency range, extract, add them all up, take logs. There you've got a nice filter bank, normally in the range of 40 to 80 dimensional feature vectors every 10 milliseconds. So that's nice, we've extracted features from it. What can we do with the word side? Well, the first thing is we're going to take those words and convert them into phones. If we wanted to build a word-based speech recognition system, conceptually, we could do it. We can just build a model for every single word. Unfortunately, the sorts of systems we run with have anything between 65,000 words and 650,000 words in the vocabulary. In order to build a model for every single discrete word, that's going to have occurrences of every single word that I want to decode available in my training data. 650,000 words, never going to happen. Irrespective of how large it's going to be, it's not going to work. So we take the word, in this case, I'm confident that no one speaks Zulu anyway, Wona, and we then convert that into a sequence of phones. So now what we're going to do is we could just base the system, rather than recognizing words, we're going to recognize phones, and then combine phones together to yield words, and then combine words together to yield sentences. But unfortunately, each of those phones is highly dependent on the context it occurs in. So to get around that, we build context-dependent phones. What that means, this is very simple, this is a triphone model. I take a phone, in this case the O, we then look at the phone to the left of it, the phone to the right of it, and that then gives us this context-dependent phone that says this is O in the context of W and N. Of course, this itself can get quite awkward. If you take a language like English, typically you might have, say, 50 phones in English. You then build a model like this, taking into account the phone to the left and the phone to the right. That gives you a total of 625,000 phones to consider. So you've actually gone back to the problem we had of not having enough words and all the words being seen to not seeing all the context-dependent phones. But that's where you use approaches that have been around for a long time. Decision tree, clustering of them, you cluster phones together, you drop them down, you ask questions such as, what is the phone to the left, what is the phone to the right? You can then build models where asking these basic decision tree style approaches, you'll always end up at a leaf of your decision tree, you just need to build a model of that leaf. So that's kind of the starting point. Then what we're going to do is, all we now need to do is to find out where that context-dependent phone exists within our original waveform. So I'm going to basically take the waveform up, splice it up into groups of context-dependent phones. Then those context-dependent phones, which I'll enforce are consistent with each other. So they've got left context is the correct left context, right context is the correct right context. Glue them together to form the words, glue the words together to form the sentence. And now, provided I can do that complete process, I can do speech recognition. So that's very straightforward and simple. By the way, I'm happy to answer questions as we go along. Don't need to save them all to the end. Yes, oh, good Lord. Maybe I'm not so happy.
Why is it the triphone has a minus on the left side and a plus on the right side?
Minus to the left, plus to the right. It's just a bizarre toolkit convention from the ages ago. It was the HDK notation. Sorry, it's sort of, yeah, minus left, plus right. Was there another question? Yes?
Can you recognize the gaps between the words by looking at the features?
Silence, yes. So basically, okay, so as I've been asked, what we've got is you kind of look at these words, and when you say this, I'm not going to actually say this sentence because I really do not know how to say that word. You can kind of think of two scenarios for what goes on between words. You've got the scenario of there is no gap between words, or there's silence between words. And the traditional approach that's used to deal with this is to basically say, if I've got a long silence, I'm building these context-dependent models, so therefore, if I've actually got a large gap here, I'm going to put a silence model to the left. So SIL is we'll treat it as a phone. So I can actually build models of silence. So I've got silence to the left context, and then the phone's associated with a word. Alternatively, I could have the fact that there is no silence in there, and then you just have this context of the context is taken from the end of the preceding word. So that's probably an I in there, so this would be W in the context of I followed by O. Anything else while we're paused? Excellent. Right, so what we've done here is really, this is one sequence, this is another sequence. It's sequence-to-sequence modeling, which is this slide. So you've actually, I believe, seen this before. You've had machine translation, where you're going from one discrete sequence, words, to another discrete sequence in another language. And again, the sequences on either side aren't going to be the same length. But machine translation, they're going to be kind of similar on the whole. Order varies, but the sequence length will be similar. Speech synthesis goes from discrete word sequences to waveforms. Well, the length of each of those is going to be remarkably different. You think about generating a sequence of 5 to 10 words, that's going to take you approximately 5 seconds. If it's sampling at 10 millisecond frame rate, that's going to give us 5,000 frames. Am I going mad here? 500 frames. And if we actually look at, so that's 5 to 10 words going to 500 frames, orders of magnitude difference. But in that case, it goes from the words discrete to the waveform. Well, for speech recognition, we're going the other way around. We're going to have things here of the length in the hundreds to things here in the 5s to 10s. So we've got this big problem of dramatically different lengths of sequences that we've got to somehow connect the two sequences together to figure out where particular elements of, well, words mapped to phones, mapped to context-dependent phones, where they occur in the word sequence. So what we're going to be talking about is I'm just going to say that the length, the feature vectors that we've extracted, that first stage that we did in the recognition process, I'm going to say that's going to be a T-length sequence indicated by X, and we're going to have the L-length word sequence indicated by this omega W. But just remember, the L is short. T is long. And that's what you've got to consider, and that's one of the worries that occurs in speech recognition. So let's look at the sort of framework of connecting all of these elements together. So we start with the waveform. We've just got some feature extraction process. And then what we've got is at the bottom here, we have the language model. And that's meant to just give me the probability of any word sequence that could occur. Valid or not, I've got to be able to produce a probability of that word sequence from that language model. So that's kind of connecting the words together. What we've then got is we've got this acoustic model up here. But that acoustic model is the model that's going to say this is the realization of a particular, well, context-dependent phone, how I expect it to be produced, how long I expect that context-dependent phone to last for. That's all produced in the acoustic model. And finally, the lexicon effectively tells me how to glue those context-dependent acoustic models together to form words, which can then be combined with, so those two combine together to yield words. We then have the language model down here, which tells me how to glue the words together. And all I've now got to do is just search over all the word sequences to decide which word sequence best matched the waveform to output R, in this case, Zulu. So it's a classic machine learning process. And when we actually look at it, we can then say, well, what's the classic machine learning solution to solving problems like that? Well, is to use Bayes' decision rule. So you say, well, I've got this, let's spell it out again. We've got features here, t-length features, x1 to t, l-length word sequences, 1 to l. Apply Bayes' decision rule. I'm trying to work out what the best word sequence is. Sorry, I've actually talking about the wrong slide. Never mind. It does happen. We'll come back to it in just a moment. So you've got those. We're going to use this in Bayes' decision rule, but for the time being, we're going to consider generative models. So what happens in a generative model? This is sort of one of the classic forms. You have a generative model that says, I'm going to produce a joint distribution of the word sequences and the features. That joint distribution of the word sequence and the features can be written as, well, the probability of the word sequence times the probability of the features given the word sequence. Well, this is our language model, how the words are put together. This is the realization of a particular set of features that we've observed. I've got the joint distribution there, and then what I want to do, well, I'm still not going to talk about Bayes' decision rule, never mind. Let's go back, and we've got the language model here. So let's actually look at a simple form of language model. Now, I believe that, again, you've learned about Ngram-style language models, where you basically say, what I want is I want the probability of this word sequence, the cat sat on the mat. So what we want to do is then say, well, we know it always starts. Well, this is a special symbol. This is a sentence start symbol. We have a sentence end symbol. The probability of that sequence is given by what we're going to do is we'll start off. We want to predict the first word, the. We'll look at the previous, in this case, single item, sentence start, and use sentence starts. What's the probability of the word the given sentence start? Then I'll move one down. We then have the probability of the word cat given the and sentence start. Now, at this point, I could keep going for the complete back history of words, but that rapidly gets impractical. Again, if you start thinking about the number of statistics that you want for this, let's give ourselves a vocabulary of 50,000 words. 50,000 words, well, if I just want it for the probability of one word, I need 50,000 probabilities in there. If I want 2 words, well, that's 50,000 squared. 3 words, 50,000 cubed. 4 words, 50,000 to the 4. These numbers get utterly impractical very, very quickly. So we'll simplify our life. What we'll do is we'll truncate the length of the back history to only have, in this case, the preceding 2 words. So then we'll say, what is the probability of the word sat given? Well, we'd say cat, the, and we'll just ignore the sentence start symbol. This actually means that we can work out for any length sentence the probability of that sentence in fixing, well, naive implementation, 50,000 cubed items. But of course, you do backing off, you do robust estimation to try and ensure that you get good estimates of all these probabilities. So what we can do is we can work out all these probabilities. Up until then, we just have the probability of the sentence end symbol given mat and the. And then we can combine them all together to say, well, what we're actually working out is the probability of the overall L-length word sequence is, well, product of each of the individual conditional probabilities. Probability of the word I given, well, if I had the exact form, it would be the complete back history. But we're going to approximate it in this case to the preceding 2 words, which is a trigram model with n is equal to 3. So there's our very simple language model. And that Ngram language model was used for many, many years. And it really was only in the early 2010s that people actually started drifting away from Ngram models and combining them with more complicated neural network-based language models. If we then shift to the acoustic model, well, again, I believe you've been told all about hidden Markov models. They're standard sequence models. They're quite easy. On the left, we've got a typical topology that is used in speech recognition. This is a 3 emitting state, left to right model. So these are the emitting states, state 2, state 3, state 4. These end non-emitting states 1 and 5, again, this tends to be linked with a particular toolkit. It allows us to very easily glue them all together, simplifies what goes on. And so what we can then say is that's the topology, 3-state, strict left to right model, no skip. Absolutely standard phone model that's used in the majority of speech recognition systems even now. On the right, I've actually put a slightly different form, which is really showing the conditional independence assumptions of a hidden Markov model. Hopefully, you're aware that what you do in a hidden Markov model is you say that the features, the probability of a particular feature is conditionally independent, given the state of that time instance, and the states are conditionally independent of each other, given the preceding state. And this sort of dynamic Bayesian network that I show on the right-hand side is there to basically illustrate the conditional independence assumptions in contrast to the model on the left, which gives us the topology of the network that we're using. So this concept of these individual states at particular time instances are going to be important to us. So what we're doing at that instance in time, we have our topology on the left, which sort of says this is one of my, well, they're going to be our context-dependent hidden Markov models. These are context-dependent phone models. They are defined by, well, 3 states, emitting states per phone. But what I'm going to do is my way to connect that to this very different length word sequence is to say, well, I'm actually going to connect them and say that each time instance I'm going to have an indication of a particular phone in, or a particular state in the whole sequence of HMMs glued together to form a sentence model. So I'm going to glue HMMs together, these context-dependent HMMs together to form words, word over all HMMs together to form sentences, and now I can say for any T-length sentence glued HMM, I can say that any particular time instance, I could have a particular state of that overall sentence model generating an observation. And what we're going to do is we're going to take advantage of this form of indicator variable to allow us to connect the words and the features together. So this goes into the HMM in a little bit more detail, again going through the maths behind the conditional independence assumption. There's our dynamic Bayesian network. What that really means is that if I'm interested in the probability of a particular state being valid at time instance t, that's going to depend on the complete back history of states if I built it that way, but we're going to say that that's truncated very much as saying I'm only dependent on the previous state in the system. So we're going to say the probability of a particular state, given the complete back history, only depends on the previous state. And that's indicated by the fact that the state indicator at time t plus 1 only depends on the state indicator at time t. Very simple model. Again, if we then look at the features, the probability of the features, given all the previous features and all the previous and current states, well, we're going to say that only depends on, well, the current state, the state at time t. And that's going to dramatically simplify our world. Again, that's indicated by the fact that the state only has an arrow going to it from the current state at time instance t. If we then glue all of that together, we can come up with equations like this. The likelihood of generating, or the probability of generating a particular set of features of length t, given an L-length word sequence, can be obtained by saying, well, we're going to take all valid state sequences of length t associated with my L-length word sequence. I'm going to sum them all together, because I don't know which one I'm going to use. I need to sum them all together. Then I just want to work out the probability of the observation sequence given this set of state sequences. Well, we've got our hidden Markov model assumption. It just turns out product over time. All of the observation features are conditionally independent given the state at that time instance, and all of the state are conditionally independent given the previous state. So this is really easy. We've converted a problem of mapping from a fixed length, say 5-word sequence, into this sequence of 500 frames by simply introducing this concept of a state indicator, dropping it into a hidden Markov model, and that allows us to work out the probability of generating a particular set of features given a word sequence just by marginalizing over all valid state sequences. That's the hidden Markov model. Everyone happy with that? Anyone unhappy with it? Anyone awake? So we'll do Bayes now. Bayes' decision rule. This is how we're going to glue it all together. Bayes' decision rule says what we want to do is, I've got these models. How do we glue them together? We say, well, Bayes' decision rule says, give me the best word sequence given the features that I've observed. Well, we know that if we can then use Bayes' rule to actually convert that, say that's the joint distribution over the probability of the features, but the probability of features isn't dependent on the word sequence. So we get this equation here, it says pick the best word sequence, the most probable word sequence over the joint distribution of words and features. But fortunately, we know that from our traditional framework, we can then take this joint distribution, say it's the probability of a word sequence, times the probability of the features given the word sequence. That's our language model. That's our acoustic model. What we've now got to do is just run this over all possible word sequences, which would seem hard. Think of all the number of word sequences you can have, but it turns out it's easy because the hidden Markov models and n-gram models both have these very, very nice conditional independence assumptions. Basically, I'm only going to go back so far on my n-gram model and then stop. Trigram, we go back 2 words. On my HMM, we only have probabilities of, well, I have probability of generating the observation is only dependent on my current state. Probability of my current state is only dependent on my previous state. We can combine all this together into a giant network where we can just run Viterbi decoding, dynamic programming. And that allows us to generate the best word sequence given the features. Now, at one point, that could have almost been the end of the talk. Go up to about 2010, I would have then spent the rest of my time telling you about the fact that we use Gaussian distributions here, the fact that this is an n-gram model, how we do discounting, how these all operate. But at its heart, that was the end of speech recognition. That was the smart bit. And then deep learning came along. Now, the problem here is this talk is a fraction out of sync. So I was hoping that by the time I gave this talk, you would all know about recurrent neural networks, and I could then just play around a little bit with them. But I'll just give you a very quick introduction to deep learning and neural networks. And like everyone else, for an introduction, you go to Wikipedia, and you read out deep learning is a branch of machine learning based on a set of algorithms that attempt to model the high-level abstractions in data by using multiple processing layers with complex structures or otherwise composed of multiple nonlinear transformations. There you go. So, why is it popular? So, what I did. So, this was actually measured in June 2016. Why it's a bit truncated there. That's 2016. I measured it in June 2016. And this goes all the way back to 1990. Anyone got an idea of what that is? I'm ignoring you. My student. No, but close. These are references to Jeff Hinton's work. And what's funny about this is that you can actually, it's quite nice because it illustrates the fact that here we had this mini sort of boom in neural networks, deep learning. We've all used multi-layer perceptrons. The M in multi-layer perceptron was many layers. So that was the first kind of blip that we had. It sort of rose, didn't really go as far as the people who worked on it would have liked. It then kind of petered around a little bit. And then here, which was around 2010, suddenly you got literally an exponential growth. And I've still not actually gone away and worked out at what point every paper is a reference to Jeff Hinton's papers, but it can't be very long. So that's kind of the growth. Everyone has their own ways, but it's sort of nice. So what is deep learning? This is a standard feed-forward network. You have an input, you have an output, you have multi-layers between the two. Each of them comprises of, actually we'll look at that. So the connection is basically, this is a typical fully connected network. Every node here, these are multiple nodes, are connected to every node here, connected to every node here, multiple layers in between, and then connected to, well, typically if we're going to do classification, it'd be a sigmoid on the output. Every layer connected to another layer. And each of those layers consists of a very simple, well, it's actually a weight matrix times the value from, so it's a weight matrix, multiply the value coming from the previous layer, add them all up, pass them through some nonlinearity. That nonlinearity then gets propagated to all the other following layers, and we just repeat that process for every single layer of your network. An incredibly simple kind of connectivity going on that yields incredibly powerful nonlinear representations and mappings, provided you can train, well, the parameters of the network are basically the weight matrices that are sitting in there. So that's a standard feed-forward network. A recurrent network, well, we're caring about sequences. We want to solve the problem of doing sequence-to-sequence modeling. So at its heart, we're going to need a sequence model. Well, fortunately, recurrent neural networks do exactly this. What we're going to do is we've got an input, as we had before, but now I've got this whole sequence going from 1 to t. What's going to happen is, well, I'd like to remember in some way some complete back history of what I've seen before. Well, what we'll do is we'll introduce a history vector. We'll call that h. And so what we've got this vector is hopefully some representation of the complete back history of every one of the inputs that I've seen before. Now what I'm going to do is I'm going to combine my complete back history with my current observation, and that gives me a new history vector, because that includes complete back history plus the current one. I've got everything now. And so what I can then do is I can then now have an output based on prediction from the complete back history of observations that I've seen. It's a great sequence model. I now pass the time delay on this history vector to make it the input for the next layer and keep repeating the process. So what's going to happen is that I can take in a t-length sequence and I'll generate t outputs at this level. If we look at a little bit more on the maths behind this, there's a couple of nonlinearities going on. We've got the fact that ht is a function of both the input and the previous history vector. Y is then a function of, well, we're just going to press those two together to give ht. The output is going to be some function of ht passed through the nonlinearities. What's nice about this, it's sort of at its heart, there are these assumptions. We want the output to be some function of the complete set of inputs in our sequence of feature vectors. So what we're going to do, well, it's split it up. We'll have that as xt, our current feature, and the complete back history x1 to t minus 1. We're going to compress those. Well, we'll take use of the history vector. We say the history vector of the complete back history is a fixed length history vector. That's the important thing. It's fixed length now, which is going to encapsulate all the important information from the back history of, well, a variable length number of features that I've seen. And I'm going to compress both of those together to give me my new history vector, which is going to give me my output. That's a recurrent neural network. It's a sequence model. It's going to be at the heart, or is one of the most commonly used aspects of deep learning for speech recognition at the moment. We drew these Bayesian networks for HMMs, dynamic Bayesian networks for HMMs, to show the conditional independence assumptions for it. So why can't we do the same for this recurrent neural network? It sort of looks like this. It's a little bit cheating. What we've got is we've got observations. We've said that the history vector at a particular time instance, here I've got ht plus 1, is dependent on, well, it's dependent on the current input, xt plus 1, the previous history vector, ht, and that then goes to determine the current output of yt plus 1. I've actually shaded it into blue. So here, the shaded numbers here, the shaded values here are observed. These are the observations that we know about. We don't know what's coming out at y. That's going to be our context-dependent HMM state probabilities. But this relationship here, normally we would have it as a probabilistic relationship. We'd have the probability. There would be some probabilistic mapping between the two. But here it's deterministic. If you noticed, if I tell you what x is, if I tell you what h is, that means that this value is completely deterministic. There are extensions to it. But this is nice. This is going to give us a model that maps from a t-length feature vectors to a set of t-length outputs. But now we're going to have the outputs that are dependent on the complete back history. And you've actually seen models like that before, HMM, CRF, and structured support vector machines. Yes, sorry.
Are you imposing
that is recycled in the current period?
So there's two ways of viewing this. In theory, you don't need to put any constraints on it. In practice, what people do, because it simplifies the training, is they sometimes do what's referred to as truncated error back propagation in time, that you actually, when you train your network, you're only going to look back over the last 20 frames or 50 frames. But in theory, no. But the real concern, of course, is that as you do this, depending on the transformation going on here, this time delay, of course, you're going to have, in the simplest form, an exponential decay going on in how far the back history comes. And that's where the more interesting models come into play, such as GRUs. Well, I'll mention them on the next slide, if I've remembered my slides correctly. Anything else at this point? So there are lots of extensions. That's really a basic model. You can actually change the structure around, so you can have a bidirectional RNN that looks at the back history, looks at the future as well, combines both the back history and the future together to allow you to make your predictions. You can introduce latent variables onto this as well. In the same way as you had latent variables in your HMM, these are unobserved things that you marginalize over. So you can have continuous latent variables introduced into your recurrent neural network, and it gives you, again, a richer set of models. They're structural changes. You can also do other changes to allow you to, for example, have a longer back history of memory for it. And so they're things like long short-term memory units, gated recurrent units, and highway connections. And I suspect you'll find out all about these things later on in the course. I'm being nodded at. Yes, you will find out. You will. So, what we'll then look at. So let's go back to our acoustic model. So what we had in our acoustic model was this hidden Markov model. So we then had this concept that these very, very simple conditional independence assumptions, the bits that allowed us to control the complexity of the models that we were using, making states only dependent on the previous state, making features only dependent on the current state. But we've then got this really powerful model, this recurrent neural network, which is going to allow us to hopefully make more interesting choices. So what we're going to do is go back to the same equation. We're going to look at all state sequences that are valid for that word sequence, because we should still marginalize over them all. And then we're just going to split it up into two parts. We've got the probability of the state sequence and the probability of the features given the state sequence. And what we'll actually look at is this one, a bit more interesting in a way of what we can do. So we've got these state sequences. Remember, the state sequences are a length tail of length t, because we've actually done the connection between the states and the word sequences by saying this is only the set of valid state sequences for that word sequence. And that's the equation that we get out for HMMs, which is a bit boring. Very little interest in there. We've only got the current state. We've actually got states, features being conditionally independent given the state, nothing of interest. So let's drop a recurrent neural network in there. And we've got a choice. This is kind of fun. We started off with our HMM. We've got this concept of a recurrent neural network. We can then sit there and say, where do we want to put these recurrent units, which are going to give us a memory of what's going on? Well, we can say, well, let's pretend we don't really care about the state history as much as the features. Let's make our life simple. So what we'll do is let's use our these memory units to remember the complete back history of features, and then say that the probability of the next feature is dependent on the complete back history of features and the current state. Well, that's exactly what this model says. This says I'm going to have a history vector. The history vector depends on the previous history vector and the previous feature. I'm going to say that the new feature, the feature that I'm going to generate, the observation I'm going to generate, that's a function of this history vector and my current state. And then I can keep propagating through. So I've kind of used this memory, the recurrent neural network history vector, to represent the complete back history of all the features, these observations that I've seen up to time instance t. And remember, we've already done our connection between the t-length sequence and the words, because it just worked. It's kind of interesting then. What's the other alternative? Well, why don't we drop it and have a back history of all the states that we've seen? Rather than having the conditional independence assumption of saying we're just going to model this, just say the feature is a function of the current state, let's put a memory in there of all the states that we've seen and run this form of model. There's actually a problem with this, and if I had more time, I would go in, because it sort of links in with recurrent neural network language models and how you do decoding with them, is because if you've got a complete back history of all the states that you've seen, then you can't run Viterbi. Because depending on what the hypothesized word sequence was up to that point, you'll have different state sequences, so I can never merge them as you do in standard Viterbi, because it's a function of everything that I've seen before in terms of the states. This one, on the other hand, well, the history vector is only a function of the observation, but the observation is the same for every word sequence. So I'm happy with that. Doesn't matter what goes on. I can actually just have that memory and run standard Viterbi decoding because I actually know what the previous observation was. So now we've dropped a recurrent neural network into our acoustic model. And we've got a memory here. Well, we'll take the standard one. We'll do the finite state. We've got a finite back history of states, but the complete back history of features. And we can then look to see what we can do with that. Well, these are the maths behind it, but let's just skip over that one. So what we've got is we've got this generative model. I've got the probability. So I should have just emphasized. So we're going to look at finite state, this one. The probability of a feature at time instance t is a function of the current state and the complete back history up to that time instance. And now what I want to do is I want to train my model and see what's going on. That's a generative model. Probability is generating an observation. Well, we could train a network to do that. So again, you may come across mixture density neural networks. We may or may not come across mixture density neural networks. That's a way of actually basically predicting distributions which can then say, you want to predict the mean of a Gaussian and the variance of a Gaussian. You can actually predict that with a recurrent neural network. And then you can work out the likelihood from that Gaussian of generating an observation. Looks like a traditional model. But more often what we do is this slight hack that we say, well, we want this. Probability of feature at time t given the state and the back history. And what we're going to do is we're going to apply Bayes' rule, probability of a state given current observation of the back history, and then we run through a series of approximations to actually get the probability of a state at time instance t. Remember, that state is one of the states of our context-dependent HMMs. Given the observation and the back history, are we going to approximate it by turning it into this pseudo-likelihood by dividing by the prior of that state. It's a pseudo-likelihood, but then we can just drop it into our standard decoding framework. We can just run everything that we ran before. So now we've got the standard. This is actually the standard form of recurrent neural network acoustic model. Along with, if it was an RNN, an LSTM, a GRU, this is the form they all have. How do we go about training them? Well, hopefully you've seen this form of equation before, where if you want the maximum likelihood estimate of an HMM, you train it to maximize the probability of generating the observation. We swap this around to estimating the state probabilities. And then what we need to do is to get the state probabilities of all time instances. Well, that's just running Viterbi to find the best state sequence given the observation sequence. And now we can just train it to, well, maximize the probability, or it's the cross-standard, cross-entropy training criterion that's often used with neural network training. This is just the sort of complicated network. This was a model that Google did in 2015. You combine convolutional neural networks with LSTM neural networks, with standard feed-forward neural networks, and you get a big, complicated network that you optimize all the parameters of your network in one go, and you get a very interesting, powerful model. So that's taken the standard framework. I could tell you all about recurrent neural network language models as well, but we don't have time. Again, people then just use recurrent neural networks in place of our standard n-gram language models, and again, that gives you nice performance gains. But rather than doing that, I thought we would look at another class of models. They were generative models, and you could swap the whole thing over and look at discriminative models. Discriminative models are quite easy. Again, this is the sort of framework that you have. Waveforms on one side, word outputs on the other side. Just going to do the traditional feature extraction. We've got a decoder, we've got an end-to-end model. This directly models the probability of any word sequence given the set of features. So we're not going to apply Bayes rule. We're just going to directly model a word sequence given an observation sequence. There's going to be issues with it, but it's quite an interesting alternative model. But we'll actually still end up going back to what we did before. We're still going to connect the word sequence and our probability of observations via these states. So we've got a state sequence here, but now we swapped it around. We've got a probability of a word sequence given the state sequence, and then the probability of the state sequence given the observation sequence. Nothing fancy, just a slightly different form. And then we're going to marginalize over that. But this is actually interesting. What does this term mean? Well, this says if I give you the state sequence associated with a particular output for a model, what's the probability of a word sequence from that state sequence? Well, that state sequence is associated with traditionally context-dependent phone models. If we glue context-dependent phone models together, that gives me the phone sequence for a sentence. We can actually set it up so that that's 1. If I tell you what the state sequence is, and I'm a little bit smart in terms of setting things up, I can make it, hopefully, ignoring homophones. We actually can get a deterministic mapping from that state sequence to phone sequences to word sequences. Deterministic. That probability is 1, and we just get left with this little term here. Probability of the t-length state sequence given the observation sequence. Well, let's actually go back to our RNNs. We want that. Let's make sure that, well, we've got the probability. Let's do another conditional independent, that the probability of a state depends only on the back history of features that it's seen. And we just run through. But suddenly at this point, we've got a standard recurrent neural network. Exactly the same recurrent neural network that we trained for our generative models. But we don't have a language model in there now. We've just got this nice little state sequence. But people have played with this. It's quite a popular model at the moment. If those of you who've read anything, one of the models that people are playing around with at the moment is Connectionist Temporal Classification, CTC. Well, CTC uses exactly that model. It just runs it through. It basically looks just like an HMM because we've got recurrency as we did for our RNN. We can still run it through. The only interesting part is really it introduces these blank symbols that people like, but you just drop them into a trellis and it all sorts of works. And some people find this is actually nice in terms of performance compared to more traditional models which don't have the blank symbols in there. Has slightly different structural aspects which can be used for standard HMMs as well. So that's one form of quite popular discriminative model. You can, of course, draw the diagrams for these. This is an old model, maximum entropy Markov models, that were used in speech recognition about a decade ago. But then CTC has, well, has this form where you've got this complete back history representation of all the features you've seen, and then your states, the probability of the states only depend on your history vector at that time instance. And you can make this more interesting by adding other links in there and having a richer history vector, but that has all sorts of problems, believe me. Not very nice. One of the things that changed on those is that we started off with this sort of phonetic sequences. We went to context-dependent phones. Could have turned that off. But what they then did is you can actually go for graphemic features. So rather than mapping your words into phones, you can map your words into how they're written. And then you can actually either do this in a context-dependent fashion. So you've got the word cat here, CAT, previous for silence, A following it, previous C, T following it, etc. Or you can just do it for CAT and actually run this at a character level, which was the original CTC style model. So it's kind of fun. People have played around. These graphemic representations are really good. We did lots of work for a wide variety of languages that you've never heard of. Just graphemic systems work quite well. And you can combine them with, there's issues with language models, but I think I'm running out of time on that. The last thing I'm going to talk about on this are encoder-decoder style representations. These are another form of discriminative model with a different form of representation of what's going on. So what you've got here is exactly the same. We want to find out the probability of a word sequence given an observation sequence. What we'll do is, well, we'll just say, let's actually just run this in a feed-forward fashion. That's the probability of a word given all the preceding words and all the t-length observations that I've got to condition it on. And what we'll do is let's make our lives more interesting. We're going to compress this down so we've got some history vector, fixed length history vector for all the preceding words. But what we'll then do is we'll actually compress the whole of our observation sequence into a fixed length vector. We'll call it C. And what we want to do with that fixed length vector, that should contain all the information that we need to discriminate between all the words. Well, if you've come across sequence kernels and aspects like that, exactly what that does. You map this variable length observation sequence into a fixed length feature vector and then run a classifier based on that. The nice thing is that now, rather than running this with a fixed specific form of sequence kernel, you can use an RNN to encode this t-length feature vector into a fixed length vector and then just decode based on that. So that's the sort of framework that people use. You sort of have a encoding RNN here, which at the end of it, you've got some encoding here of the complete back history of all the observations that it's seen. You can then actually condition your decoding stage, which is to find the best word sequence. You can actually condition that on this encoding of the observation sequence. And now you've got a nice, very simple thing that you can actually optimize every parameter in one go. There's a problem because the actual encompassing of this actually is a really painful job to do. It's got to encapsulate all the information of the complete acoustic feature vector sequence to encapsulate all the information to get the decoding going well. So it didn't work very well. So they introduced attention, and you're going to find out all about attention possibly later in the course. If you don't find out about attention later in the course, it's a really interesting thing to look at. So what it does is rather than saying we're going to have one conditioning vector, and that one conditioning vector is used for every single word, we're going to let the words learn, or the system learn, which elements of the feature vector are most appropriate for the decoding of that word, the attention mechanism. And then so what we're going to do is we're going to encode, still encode our features into these history vectors, but we'll then use an attention mechanism to pick which of the history vectors a particular word cares about, and then we decode with it. And if you wanted the maths, it's that. But you may or may not find out about that, so we'll move on. Conclusion. It's interesting time. It's kind of fun. There's lots of options. I've just gone through really quickly just some of the options that people care about for acoustic models, for speech recognitions. We've not spoken about language models. We've not spoken about all the options of all the criteria that could be used to train these systems that tune them not to try and best the best sentence sequence, but they might be a task-specific metric, might be a word error rate metric. It's sort of fun. There's a lot of things going on in speech at the moment, well beyond n-grams and HMMs. So it's sort of fun. Currently, still the state of the art really is. You look at most systems, they are still generative. All the fancy models that people would like to use, they're still not beating the original standard models that are out there. But they're generative models making use of deep learning for feature extraction, deep learning for language models, deep learning for acoustic models. All optimized with very, very interesting criteria. Now, what I was going to do is, while I answer any questions that you may or may not still be awake to talk to me about, I was going to play a fun video. Not a fun video. It's not actually a fun video at all. But it's this, which I find slightly hypnotic. So what you've done, this is one of my students' work, which is why I'm kind of playing it. Because it's a bit of, so on the left, you take a layer of your network, and it's kind of normally just written as a vector. Of course, it's a highly distributed representation. There's no structure in it. You can reorder the nodes in a network. No one cares. What you did, took the nodes, 1024, reordered them into a grid, and looked at the outputs of the activation from it. And that's the one on the left here. So utterly all over the place. So we read this through. It's actually going through the activation, reading it's a sentence from the broadcast news evaluation task from 20 years ago. And what we did is we sort of said, well, we don't like that. What we'd like to happen is we'd like to say, when we've got a particular phone, I'd like this region to light up. And then got a different phone, I'd like this region to light up. Oh, I thought it was on a loop. Let's play it again. I like it. Because it distracts people. And then we said, let these regions, and then we trained a system. And this is sort of fun. You then get this weird blobs. These are activation function outputs. And they move around. Now that sort of sounds fun. You know, you can sort of say, it's pretty. And you don't get many nice, pretty videos in speech talks. They're equations, or you might listen to something if I had audio at best. So I thought but then what's really fun is this actually helps speech recognition performance. Because what you're doing is you've got a really smart form of regularization. Normal regularization is, well, if you took L2, that's really dumb. Let everything be 0. Why? So do something smarter. Do dropout. That's fun, but it's all a bit random. Let's just hope it works. It does a lot of the time. But this, come on, keep it going. Is there a loop button somewhere? Nah, keep going. So, but this actually says what we'd like is let things be high here. Let things be high here. And it gives you nice, smooth surfaces. You can actually run these, and it helps. We actually did this for the last Babel evaluation. All our final systems use this, based on graphemes and lots of other weird things. Right, so while that's playing, any questions? Yes?
So what's actually the difference between the left and the right one?
That one is basically, I've told it to make that region down there. I've said, when you've got a phone A going, I want this region to be high, and have high activation functions. All the rest to be low. So basically took the KL divergence of a normalized activation functions for that layer, and said, take the KL divergence and just actually regularize it, make it look a little bit like this. Use Tiesner to determine where things were meant to be, and then just trained it. It's all just fun. Yes?
I actually have 2 questions. First one is a fast question. So basically, in the last part of the first section, you try to reconstruct the likelihood and joint distribution from this post distribution from a neural network.
Yeah.
I want to ask what motivates us to do that?
Because what you could do is you could train a nice neural network using standard neural network training with cross entropy and drop it into your standard HMM decoding framework. So that's the motivation that people originally had for it. For those of you who have played around or know about synthesis, things like WaveNet, there's also the assumptions behind things like WaveNet, which also runs synthesis as a classification task, because it really says, we don't believe the world is Gaussian. So I could normally say, well, let's train a network to predict a mixed density neural network, to predict Gaussian distributions from it. But that's making the assumption that our features are in some way Gaussian. No, not necessarily. So what's the alternative? What makes us allow to say it's not Gaussian? Well, we'll actually build it as a classifier. There's no assumption of the world being Gaussian there. So there's that other side aspect that I don't know whether, no, that was done way back in the early 90s when neural networks had their first breach. So I don't know, I've never asked whether that was one of their motivations for it as well.
Okay, thanks. And the next question would be a context question. So from my understanding, for the whole introduction, it's mainly about the map from the phone to the text, right? So, but recall that the human speech system actually is quite instinct in the sense that even a children can speak and can listen before they are taught to read and write, right? So I'm wondering whether it's possible to directly build some system directly from the phone to some understanding, for example, task classification. So basically we classify the phone to some class whether it's possible to directly do the direct map and to gain some performance.
So this is one of the interesting areas at the moment. I've described this in terms of how we do speech recognition, and when I said this was an end-to-end system for speech recognition, that was basically, I described it as a posterior model. It's really saying let's train all elements of the speech recognition systems in an integrated fashion against a common criterion. Word error rate, minimizing an expected word error rate. But you can actually take this beyond there. So when people are starting to looking at things like spoken machine translation systems, speech translation, well, there they're saying, well, why should I lock myself to having words as some intermediate representation for my speech recognition system to produce words, and then take words to produce a system for translation. Let's lock it. Let's actually build a system that has no assumption about words being the connection between the ASR system and the translation system, and just integrate it. So that's really one of the lines that people are very keen on, these integrated end-to-end trained systems. So, yep, people are doing exactly that. Effectively, solve this task for me. And if the task consists of multiple modules, forget about that. Train all the modules of the system in an integrated fashion. And just pray you have enough training data. Yes?
So a question is, do you think there's some, or have you considered any unsupervised method for training neural nets for speech recognition which don't rely on fixed alignments as an initial stage?
So this, yes. So this is, so what people have done. I'm bored with that as well. Let's go back to let's pretend we were back on the slides again. So the real question is, so this is actually, again, there's some interesting work came out from Dan Povey. If you played around with a Caldi toolkit, it's a very nice toolkit. Not as well documented as HDK, of course, but it's a good toolkit. I'm associated with HDK. But there you actually you try to get rid of the assumption of the hard alignments from the initialize the models with a cross-entropy criterion. It's really coming down to how do you initialize a model and how robust are they to initialization. And that's a major problem. So Dan does purely sequence-trained system. He claims it's less sensitive to some of the initialization aspects. But one of the original motivations was pre-training, how you initialize these systems. I don't know what the answer is. There are these ones which you hope will overcome the fact, let's just randomly initialize the network parameters, let the system train, it should just optimize to a correct point. But we are still incredibly sensitive to initialization, incredibly sensitive to hyperparameter selection. It can all go horribly wrong. And it's a complicated connection. You're going up orders of magnitude difference between word sequences and feature sequences. And it's that difference in length that can cause us problems.
Okay.
So I have one question, which is, I saw the ellipses on one of your last slides. I think this is referring to interspeech, right?
Which one?
Those ones in next conference in August, right?
Yes.
Are you, because, I mean, so the big change occurred like in 2010, right? Then we have been having improvements. Do you see something big again coming in the future? Are we going to have to change everything all over again, or are we kind of stable? I mean, it's because in the NLP community, they're experiencing this right now. So NMT became the new state of the art just now, like a couple of years. And in speech, it has been like more or less stable now. Are we on the edge of some new jump? What do you think?
If I knew the new jump, if I knew, I would not tell you. See my papers, but no. I think it's interesting. All these approaches are fairly generic approaches. They are nonlinear mapping processes with all the strengths of nonlinear mapping processes and all the issues with nonlinear mapping processes. So whether we get something better than, well, a recurrent neural network, very nice, simple model of how to encapsulate a complete back history into a fixed length vector. People then played around and had gating on top of that to yield LSTMs for a better history representation for a longer back history. They then introduced highway connections to allow you to skip over particular time instances. You might have residual networks to allow you to skip over layers of networks. These all, it depends how you view whether these are tweaks or not, but they really, you know, in some ways, the concept of how we start learning to structure networks better so that we don't every single time we get a new network to train, we go to our bunch of students, we lock them in cupboards, we only let them out of the cupboard when they improve the performance, send them back to the cupboard, which basically is almost the model that we run. You basically get there, someone gives you a task, you do a sweep of hyperparameters with your favorite network topology, you then sweep over your favorite network topologies. I think the next thing is for us to try and learn how to make better use of prior knowledge within network topologies. So it's not a fundamental stage. It's not saying, let's get rid of generic nonlinear mappings that handle sequences or not. I think it's the challenge we've got now is the fact that we just reset almost every single task.
So strong priors, like having strong priors to...
Well, it's actually, the problem is having priors on, it's hard enough trying to get adaptation to work for these sorts of systems because we have so little information about what the parameters of the network learn. So trying to say we want strong priors on the network parameters is really tough.
Yeah.
Having appropriate forms of regularization, you know, the example of the nice things moving, this is trying to look for smarter forms of regularization, which I hope then will make it less sensitive to, again, the forms of initialization that are required for these systems, the nature of the optimization, therefore the sweep of hyperparameters.
Okay, thanks. Any other question? Then otherwise, let's thank the speaker again. And remember.